in module 7, we talked mainly about the Hurwitz-Thompson estimator, its formation, expression for its variance and the variance estimate. But there are a lot of things to be taken up, and in module 8 we continue with those notions and we review some of the results already discussed, and we go ahead mainly with the problem of estimation of the variance, be it of the Hurwitz-Thompson estimator or of any other arbitrary estimator, and then we will see how the results simplify in case the sampling design is a fixed size sampling design. So long we just based our results on the computation of pi I and pi ij without any regard to the nature of the sampling design, whether it is fixed size or variable size. But as you know, in this context, a sampling design, it is a broad based notion of sampling design. The description of the samples could be of arbitrary size. Therefore, the results are very general. When you specialize to fixed size sampling designs, there are simplifications, and that is what we are going to talk about here. So, let us see how the results are coming in. So, having understood the formation of the Hurwitz-Thompson estimator and also an expression for the variance of the Hurwitz-Thompson estimator, what is your next question?
So the next obvious question, I believe, is that of estimation, unbiased estimation of the variance of the Hurwitz-Thompson estimator from the sample data based on a given sampling design. I guess so far we are discussing the case of an entirely arbitrary sampling designs, admitting of pi i's positive for each I in the population. So how do we go about it?
Well, recall how the population total was unbiasedly estimated and why we needed the condition pi I strictly positive for each I, and how it was utilized in the formation of the Hurwitz-Thompson estimator. You pointed out that Ty, which is summation yi, can be expressed as summation yi over pi I times pi I. You keep yi over pi I, and the other pi I in the numerator you replace by the inclusion probability definition, sum over I belonging to S, sum over all S containing I Ps, and then you twisted the two and you came up with an estimator of the population total, which was summation yi over pi I for all I in the sample, and that was the Hurwitz-Thompson estimator. So you apply the same trick here. You know the variance of the Hurwitz-Thompson estimator, it comes in two parts. One part involves the squares, other term involves the product terms. So for the square terms, you divide by pi I, multiply by pi I, replace pi I by summation Ps over all S containing I, etc. And for the product term, you mimic the idea. For the product term, you replace yi into yj by yi yj over pi ij times pi ij, etc. So let us see. Because the variance has two parts, the first part involves yi square. It is as if we are mimicking the formation of the HT for the population total. So we estimate the first term, which is summation yi square over pi I square by summation yi square over pi I square times 1 minus pi I.
So likewise, the second term is estimated by, well, looks like we need another set of conditions now. That is, I guess we also need pi ij strictly positive for all pairs of units ij in the population. And when this is ensured, we have the estimate summing over I not equal to j in the sample, yi yj divided by pi I pi j multiplied by pi ij minus pi I pi j divided by pi ij. Adding the two, we have a variance estimate for the Hurwitz-Thompson estimator. So far, I understand all this. Is that all for our data analysis? After all, I do not know what else is to be done here.
Okay, Gupta, it is only when you carry out an actual data analysis and variance estimation computation from an actual survey data, you appreciate the continued efforts by survey sampling researchers for selecting a suitable sampling design. At this stage, let us take a very simple illustrative example. I am referring to a hypothetical example of 6 units in the population, a fixed size sampling design of size 3, You can see there are all kinds of samples of size 3, starting with 1, 2, 3, going all the way up to 1, 5, 6. It's not that I have picked up all triplets. All triplets are 6 combination 3, which is 20. I did not pick up all triplets. I picked up selected 7, but I made sure that all the pi i's are positive, yes. I also made sure, hopefully, that all the pi ij's are positive. Anyway, I have attached probability 1 over 7 to each of these 7 samples. And now I can go ahead comfortably with the computations. So here you find pi 1, pi 2, pi 3, pi 1, 2, pi 1, 3, pi 2, 3. Sample actually selected, suppose through implementation of random sampling technique, we have selected the sample 1, 2, 3, and you have got the y values like 30, 70, 35. Therefore, your Hobson estimator is y1 over pi 1 plus y2 over pi 2, etc. Very easy computation. And you can also work out the estimate of the variance by using the formula that you mentioned, and you find to your own surprise that it is a negative point. What is the lesson for us, Gupta?
Well, I think if we go back to the variance estimate of the Horvitz-Thompson estimator expression, we find a multiplier, pi ij minus pi I pi j, and so on. Maybe we should make sure that this quantity is non-negative. I don't know, it does not seem to be obvious to me now. Sort of confusion.
Okay, let me throw some light on this matter. Note that in the example above, we are referring to a fixed size design, sample size being little n. First note that for this kind of design, sometime back in one of the modules, I mentioned and we went through these particular relations involving the first and second order inclusion probabilities with reference to fixed size design. If the sample size is small n fixed for all samples, then sum of the inclusion probabilities is equal to little n. Then the third relation says double summation pi I j over all I not equal to j is n into n minus 1, and the second relation is something relating to pi I for fixed I. That is, those are the relations that we know. Using these relations, the expression for the Vidya-mitra estimator variance, the expression that we have seen before, that was originally given by Horvitz and Thompson, using these relations with reference to unequal probability sampling, fixed size sampling designs, the expression was simplified further to what you find here, and that is due to Sen, Yates and Grundy. Yates and Grundy, they had a joint paper, and Sen did it independently. That's why you call it Sen, Yates, Grundy, and that is the variance expression for the Horvitz-Thompson estimator. The expression due to Sen, Yates and Grundy, double summation yi over pi I minus yj over pi j whole square times pi I pi j minus pi I j. And therefore the obvious variance estimator is nothing but you restrict to the sample and divide by pi I j. That is what is written in the next line. That is the estimate of the variance of the Horvitz-Thompson estimator under Sen, Yates, Grundy formulation, but this is valid only when the sample size is a fixed size sample design. The moment you find it here, now you see that pi I by j over pi I j minus 1, that has to be, if that is non-negative, because the last part being a square, there is no problem. That's what gives you the condition. So once this expression is understood, you can see that a sufficient condition for non-negative variance estimation is pi I pi j greater than or equal to pi I j, because that is exactly the quantity that is coming in the expression for the variance estimation. So what is the lesson? If we are dealing with a fixed size sampling design, it is always advisable and recommended that you come up with a sampling design that will be thoroughly arbitrary, but for the fact that all pi ij's are strictly positive, and moreover pi I pi j is then equal to pi ij for all pairs I and j. If that happens, then you know that under a fixed size sampling design, your expression for the Sen, Yates, Grundy variance estimator is going to be non-negative, because that condition simplifies to non-negativity of pi I pi j minus pi I j. And of course at the end, data driven quantity is a perfect square, so you have no problem. I believe I am going a bit slow in exposing these topics. I don't like the idea of rush. There are so many things to be taken up one by one. The topics are interesting and I want to make sure that you are motivated to understand the matter and the material, and also to take up some research problems in future. So in this module, what we took up basically is the variance estimation problem, that there are two components of the variance for any unbiased homogeneous linear unbiased estimator of the population total, be it Hurwitz-Thompson estimator or any other estimator. Because the estimator is homogeneous linear, variance expression is homogeneous quadratic, it involves yi square and the product term yi yj. For estimation of yi square term, we need pi I positive. For estimation of yi yj product term, we need pi ij positive. But that is not enough. An expression for the estimate of the variance, once it is written down, we need some kind of assurance that when we actually adopt the sampling design, collect the data, come up with at the estimation stage, we want to make sure that we have an estimate with non-negative variance estimate. That is a big problem in practice. Nobody likes, and it is very difficult to convince the user about the variance estimate being negative. So we have to give a protection towards that, and for that we have seen that a sufficient condition is pi I times pi j greater than equal to pi ij, and that of course has to be greater than 0. Therefore, the last thing said that a sufficient condition for non-negative variance estimation pi I pi j greater than equal to pi ij greater than 0 for all I not equal, for all pairs. That is the condition if we can ensure while dealing with a fixed size sampling design. So other than that, we are not stipulating any condition whatsoever. All we want is that the pi i's should be positive, pi ij should be positive, and further that pi I times pi j should be greater than equal to pi ij. For a fixed size design, that will ensure non-negativity of the variance estimator, at least so far as the Hurwitz-Thompson estimator is concerned. Now it is very interesting to note that for simple random sampling with without stratified, and then PPS with without, everywhere this condition it is valid, but we are referring to simple random sampling without replacement, stratified without replacement, PPS without replacement, to be able to use the Sen-Yates-Grundy formulation and to be able to claim non-negativity of the variance estimate once we verify that pi I pi j greater than equal to pi ij greater than 0. And that is surprisingly and interestingly, that is indeed true for all these standard sampling designs. Now we will take up some questions and MCQs. We have altogether 3 questions here. Let me read out. Under simple random sampling without replacement sampling design, population size capital N, sample size small n, standard notation, using suitably the results based on the Hurwitz-Thompson estimator, derive that the sample variance is an unbiased estimator for the population variance. So the derivation that you are supposed to make, it is already built in here. It says using the results of the Hurwitz-Thompson estimator. So Hurwitz-Thompson estimator of the population mean, it has an expression for the variance, and that variance estimator is also there, and all these things are built in. Variance of the Hurwitz-Thompson estimator of the population mean, that is given by 1 over small n minus 1 over capital N capital S square, and estimate of that variance is given by 1 over small n minus 1 over capital N small s square. Therefore, it follows immediately that expected value of small s square equal to capital S square. In other words, the sample variance is an unbiased estimator of the population variance. That follows almost trivially once you look at the expression for the variance of the HT and V hat HT for a sample drawn from a population according to SRSW. This is a very straightforward question. Question number 2. For PPS without replacement sampling of sample size 2, provide an unbiased estimator of the population variance. Is it necessarily non-negative? Good question. When it says provide an unbiased estimator of the population variance, the tricky part, if you can say so, is that once you know that the expression for the variance of the horizontal estimator under a fixed size design, it has a component yi by pi I minus yj by pi j whole square. We have learned, at some stage you have learned, maybe your undergraduate first year or maybe in second year, somewhere down the line, you have learned that an expression for the variance involves double summation yi minus yj whole square. So first you express the population variance as double summation yi minus yj whole square with a multiplier. Once you know that, then you know to estimate this quantity yi minus yj whole square has to be divided by pi ij, and that is where I and j come together. So it is a straightforward derivation of an expression for an unbiased estimator of the population variance rests on the fact that the population variance can be expressed as a multiple of double summation yi minus yj whole square. And therefore, an unbiased estimator for this is the same multiplier multiplied by double summation restricted to the sample yi minus yj whole square divided by pi ij. Once you know that, it's just a matter of figuring out pi ij, whether pi ij is non-negative or not, and you know under PPS without replacement sampling for a sample of size 2, you know the expression for the joint inclusion probability pi sub ij, and you know trivially that it is non-negative. Therefore, this question, the answer to this question is yes, and you can very easily provide unbiased estimator of population variance, but you have to do that basic homework, representation of population variance as a multiple of double summation yi minus yj whole square. Is that okay, Gupta?
Yes, sir.
Okay, next question. Consider without replacement n sampling. It does not say simple random sampling or PPS or whatever. It says without replacement sampling design. That means all the units are distinct in the sample in the following manner. Now it says what you are doing. First unit is drawn according to P1, P2, Pn. The rest are drawn by without replacement sampling. So you are told how you are picking up a sample of size n without replacement from a given population by using the procedure under A. And the procedure under B is the first n minus 1 units are drawn according to without replacement, the last one by effective use of P1, P2, Pn. Note the phrase effective use, that's because all the previous small n minus 1 they have to be discarded, and you have to use the PIs for all those who are left. So you have to make use of adjusting the PIs. We have been talking about this thing for some time. In both the cases, work out estimator of the population mean, variance of the proposed estimator, estimator of the variance so derived, comment on your findings. Very interesting. So eventually you are talking about computation of pi I, pi j, pi ij, and verifying that inequality, whether pi I, pi j greater than equal to pi ij greater than 0. Okay? You are landing into essentially that problem. Okay. We have some multiple choice questions. Please read.
The population variance and biased estimation is possible whenever the sample size exceeds 2 in any without replacement capital and small n sampling. True, false, or does it depend on the sampling design even if n is more than 2?
That's interesting. If they are talking about population variance unbiased estimation, so I need pi ij strictly positive, therefore small n has got to be at least equal to 2. It's not that small n has to exceed 2. Okay, so small n can be at least equal to 2. But then small n equal to 2 is not enough. I need a condition on the sampling design to make sure that all pi ij's are positive. Okay? What is the next one?
Population variance non-negative unbiased estimation is possible whenever the sample size exceeds 2 in any without replacement capital and small n sampling. True, false, or does it depend on the sampling design even if n is more than 2?
So they are talking about non-negative unbiased variance estimation. The first thing is unbiased estimation, then non-negativity. Unbiased estimation needs at least 2 observations, distinct. So whenever the sample size exceeds 2, you don't need exceeding 2. 2 is also good enough, provided pi ij is strictly positive and the condition for non-negativity holds. What is the next one?
Population variance and bias estimation is possible whenever 1. The sample size exceeds 2 in any without replacement sampling design and for the chosen sampling design. 2. Pi TS is more than 0 for all pairs S not equal to 2. True when both 1 and 2 are valid?
They are giving several options. Very good. The first one refers to sample size exceeding 2 and the second one refers to for all pairs S and T, pi S T joint inclusion probability strictly positive. And they wanted to know that this statement is to population variance can be adversely estimated provided there are so many options given. Okay? So you know how to go about it. Interesting. Do I have anything else? Okay, there is one more. Okay.
For unbiased variance estimation under without replacement sampling, it is trivially true that pi TS's are strictly positive for all pairs of units captured in the selected sample, and this is true for every sample in the domain of the definition of the without replacement design. Therefore, we do not need any further condition to this effect. This argument is true or false or true, subject to the proper choice of the without replacement design.
Okay, let's try to understand the question. For unbiased variance estimation under without replacement sampling, it is trivially true that for all the pairs of units captured in the selected sample, pi ij's are positive. We will agree with this thing. If my sample has got the units 1, 3, 7, so probability of getting 1, 3, 7 must be something positive. Therefore, pi 1, 3, pi 1, 7, pi 3, 7, they are trivially positive. That is the first sentence says. It is trivially true that pi TS's are strictly positive for all pairs of units T and S captured in the selected sample. And this is true for every sample in the domain of definition of the without replacement design. I have a definition where all the samples, wherever the samples are listed, every sample has a positive probability and all the constituent members in every sample pairwise they all have positive probability. If that is the case, why do I need any further condition like pi ij greater than 0 for all I not equal to j in the population? It's very tricky, good problem. So they are saying maybe I don't need any further condition because in my sample, all the sample units captured, all the units captured in a sample, they have definitely positive pairwise inclusion probabilities. So why do I need any further condition? The condition that we have been learning is pi ij is strictly positive for all I not equal to j in the population. Why do I care about the population at large? It says the argument is true or false or true subject to proper choice of the without replacement design.